In this lecture, I will discuss two-dimensional kinematics, and the quantities that I will introduce here are just an extension of the quantities discussed in the previous chapter, which was one-dimensional kinematics. I will also talk about a specific type of two-dimensional motion, which is the projectile motion. I wanted to start the lecture with explaining the transition from one-dimensional quantities, more specifically the displacement, velocity, and acceleration, into two-dimensional quantities. In the one-dimensional situation, I defined the displacement of an object as it moves on a straight line, the average velocity, or simply just the velocity of the object, and the acceleration of the object. So if I would try to depict these vectors in space, I need to introduce a one-dimensional coordinate system with a positive orientation and negative orientation, and then also an origin in this coordinate system, and from there I can measure the displacement. I can also indicate the velocity and the acceleration, and all of that happens in one dimension. Now, when we switch to two-dimensional considerations, these three vectors will have components along the x direction and along the y direction. In a two-dimensional problem, all vectors will be presented in a two-dimensional coordinate system, which will have two coordinate axes, an x-axis and a y-axis, with positive orientations to the right for the x-axis and up for the y-axis. The displacement vector now is labeled with r, is a two-dimensional vector. So that means that this vector can be presented as the sum of two vector components, which I will call delta Rx and delta Ry. And of course, if I introduce unit vectors to this representation, x hat and y hat, then the displacement vector can be also written in unit vector notation as delta r is equal to delta Rx, the magnitude of the vector component, times x hat, plus delta Ry times y hat. And so this is the unit vector representation of the displacement vector, which is a two-dimensional vector. Similarly, I can also represent a velocity and acceleration vector in a two-dimensional coordinate system. The velocity vector can be presented in unit vector notation as Vx x hat plus Vy y hat, where Vx and Vy are the scalar components of the vector. And the acceleration vector can be presented in two dimensions in unit vector notation as Ax times x hat plus Ay times y hat, where Ax and Ay are the scalar components of the acceleration. So as you can see, the notation here looks pretty much the same as the notation that I used in general for vectors when I wanted to present them in unit vector notation. And so the rules for these three specific vectors are exactly the same as the general rules for vectors that I talked about in chapter 1. Now let's focus a little bit closer on the displacement, velocity, and acceleration vectors. So here we have an object, a race car, that is driving on the road, and it's not on a straight line. There is a curve here. And so I can determine the positions of the car at two different points along the turn. So the initial position is given by the two-dimensional position vector r0, and the final position right here is given by another two-dimensional position vector, which I call r. And so the displacement of this car is the straight line distance from the initial position to the final position, just like the standard definition of displacement. And that displacement vector delta r will be equal to the difference between r and r0. But now remember that those are two-dimensional vectors. So when this difference is actually calculated, it will have to be done by components. So let's write down by components how this difference is calculated. So for the resultant vector, the x component will be the x component of r minus the x component of r0. And the y component will be the y component of r minus the y component of y0. So this part here is delta rx, and this part here is delta ry. So the rule for addition that I explained in chapter 1 is the same applied for the displacement vector. I can define average velocity similarly to the way I defined it in the one-dimensional kinematics chapter as the displacement between initial and final positions divided by the elapsed time for that displacement to occur. In other words, that will be r minus r0 divided by t minus t0, or delta r divided by delta t. And here again, when calculating this average velocity, we must go back to the calculation of displacement, which is shown here. Take this result and divide both terms by the elapsed time. And so then by components, the average velocity vector v is equal to rx minus r0 x hat divided by t minus t0. And that part here essentially is the x component of the velocity vx, plus the second term is ry minus r0y divided by t minus t0 y hat, and that second term is the y component of the velocity vy. So this relationship here gives us the opportunity to calculate the average velocity of motion when we only know the initial and final positions as two-dimensional vectors, and therefore we know their components in the x and y direction, and we also know the time, the elapsed time between the object being at the initial and final positions. So this method here gives us a very powerful tool to calculate velocity vectors. The average acceleration in two dimensions can be defined exactly the same as the average acceleration in one dimension, as final velocity minus initial velocity divided by elapsed time, but now keeping in mind that the velocity vectors are two-dimensional vectors. And so the change in velocity can be sketched as a vector sum as the following vector triangle. So here we have the final velocity v, the initial velocity v0, and then v minus v0 is equal to delta v. So let's talk a little bit more in detail of how this triangle comes to be. So I will start with a two-dimensional coordinate system, x and y. And now let's draw the initial velocity vector starting at the origin of this coordinate system. So this is the initial velocity vector. So now let's imagine that there is a influence that causes this moving object to have acceleration along this line. Well, what that will do is it's going to cause this object to start going around a turn as it's moving in that direction. Okay, so basically what this motion will look like will be something like this. And so later on, the velocity will point in some other direction, not the original direction of the original initial velocity. And so let's say that this new velocity is directed like so. And so I bring that vector also to start at the origin of the coordinate system. So now I'm ready to draw the vector that corresponds to the change in velocity delta v. And so, one more time, the initial velocity has this direction, but because an influence is acting on the object to make it accelerate like so, the object ends up having a different velocity after some time, different in both magnitude and direction in general. And so as a result, the change in velocity is this vector, which then closes this triangle. So this vector here was calculated by using the standard rules of vector addition as the difference between v and v0. So why did I sort of assume that there was acceleration acting in this direction? Well, because the acceleration is a vector quantity, and the acceleration is parallel to the change in velocity vector. Okay? And so, in order for the change of velocity to happen from v0 to v in the way that I showed, the acceleration vector must be directed in that direction. It's in the same direction as the change of velocity delta v. The equations of kinematic in 2 dimensions, when the acceleration is constant, are exactly the same as the equations for 1-dimensional motion, with the difference that now each of those equations, since they involve vector quantities, will have 2 coordinate representations. So we can write each of those along the x-axis and along the y-axis. So I'm going to list those options on the left and right side, and to differentiate which axis I'm talking about, I will index each variable that is a vector quantity with the appropriate index corresponding to that coordinate axis. In the x-axis direction, the equations right indexed with the x-axis as vx is equal to v0x plus ax times t. So each vector quantity gets an x component index. X is equal to v0x plus vx times t. Vx squared is equal to v0x squared plus 2x times x. And then finally, x is equal to v0x times t plus 1/2 ax times t squared. And then along the y-axis, I index everything for the y-axis. So vy is equal to v0y plus ay times t. Y, the vertical displacement, is equal to 1/2 v0y plus vy times t. Vy squared plus v0y squared plus 2 times ay. And then finally, y is equal to v0y times t plus 1/2 ay times t squared. So these are the general kinematic equations in 2 dimensions, broken down by axis orientation. And so when you're doing problems in 2-dimensional kinematics, you will always have to break down the equation into x and y direction equation, of course, if the problem requires that, and work by components like that. The reason why such separation by coordinate direction is possible is because any 2-dimensional motion can be looked at as the sum of 2 1-dimensional motions, one along the x-axis and one along the y-axis. Let's look into that in a little bit more detail and explain it. Let's consider an object that starts its motion at the origin of a 2-dimensional coordinate system, and then it undergoes some motion along a curved trajectory, and it ends up at this position later in that 2-dimensional space. So what are the possibilities of this object getting to that final position here? Well, there is 2 options. One would be to move horizontally along the x-axis until the object reaches a position right below this two-dimensional position and then go up until it reaches that position. So the trajectory would look something like this, or the path will look something like this way, and then this way. Of course, there is also the possibility of going first vertically up and then horizontally to the right until the object reaches that position as well. So vertical motion first and then horizontal motion after that. So 1, 2, 1, 2. Well, so that exactly looks like what I just explained. We can consider the motion of the object as two independent motions, one in horizontal direction and one in vertical direction, but both are happening at the same time. And so as a result, the object is moving along a trajectory that looks like so. So it's not a straight line, but rather it's a curve, because the motion horizontally and vertically are not exactly identical in general. If the two motions were exactly identical, then this trajectory would be exactly a straight line. So, but this is a special case situation, so we cannot discuss special cases when we want to explain general rules. And so then, in horizontal direction, all the formulas will apply with the appropriate index. So, for example, Vx is equal to V0x plus ax times t. X is equal to V0x times t plus 1/2 ax times t squared, and so on and so forth. And then vertically, I can write the same thing with the appropriate indices. So Vy is equal to Vy0 plus ay times t. Y is equal to V0y times t plus 1/2 ay times t squared, and so on and so forth. And then combining those sets of equations together give us the parameters for the combined motion or the total motion of the object at this point. So that is the idea. Now let's look at the following example to illustrate the points that I made about a two-dimensional motion being the sum of two one-dimensional motions. In the x direction, the spacecraft below has an initial velocity component v0x equal to 22 meters per second and acceleration of 24 meters per second squared. In the y direction, the analogous quantities are v0y equal to 14 meters per second and an acceleration of 12 meters per second squared. At a time equal to 7 seconds, find the horizontal displacement x and the x component of the final velocity, this one right here. And then also at the same time find the vertical displacement y and the y component of the final velocity. And also find the final velocity of the spacecraft. So the final velocity would be like that. So we want to find the magnitude and also the angle that it makes with positive x direction. So these are the questions that we will answer. So I can make two tables with the quantities that the 5 kinematic quantities indexed for each coordinate direction. And so as you can see, for the x direction, we have the horizontal displacement, acceleration in x direction, final velocity in x direction, initial velocity in x direction, and time of travel. And so for the x direction, I know the horizontal acceleration and the initial horizontal velocity and the time of travel. The same I can do for the vertical portion of the motion. So I have the vertical displacement, which I'm looking for. I have the acceleration in y direction. I'm looking for the y component of the final velocity. I know the initial component of the vertical velocity, and I know the time of travel. So for each direction of motion, I'm looking for two unknowns, and I know the other three variables. So first, let's do the x direction. So since I know the acceleration in x direction, the initial x velocity, and the time of travel, I can use this kinematic equation to find the horizontal displacement. So v0x times t plus 1/2 ax times t squared will give me the horizontal displacement. And so if I substitute the values that I know into that equation, I get that the horizontal displacement is 740 meters in positive x direction. I also want to find the x component of the final velocity of this spacecraft after 7 seconds. So this kinematic equation here will give me that answer. So Vx is equal to V0x plus ax times t. Substituting the values in the formula gives me the final answer, which is 190 meters per second in positive x direction. So then I apply the same procedure for the y direction. So again, I want the vertical displacement and the final velocity y component. So I use again the same two kinematic equations as before, but this time indexed for the y coordinate direction. And so when I substitute the quantities in those formulas, I get that the vertical displacement is 390 meters in positive y direction, and the y component of the final velocity is 98 meters in positive y direction. So since I now have the components of the final velocity, I can put them together in a triangle like the one showed right here, where Vx is the adjacent side, Vy is the opposite side, and then V is the hypotenuse. And now I can use the Pythagorean theorem to find the magnitude of the final velocity V. And so the magnitude of the final velocity V is equal to the square root of the square of the x component plus the square of the y component, or the final velocity is 210 meters per second. And since that's a vector quantity, I also must give orientation with respect to the horizontal direction, the positive horizontal direction. And so that angle, theta, is going to be equal to the inverse tangent of the y component of the velocity divided by the x component. So that is 98 divided by 190, or that is 27 degrees. And so when I know those two numbers here, that completely defines the final velocity vector of this spacecraft. A very important special case of two-dimensional motion is the projectile motion. Projectile motion is the motion that any object that is thrown above ground undergoes. For example, a baseball has been hit by a bat, a basketball that somebody shoots into a hoop, a football that's thrown by the quarterback, a frisbee that's thrown in the air, and so on and so forth. Projectile motion is a two-dimensional motion, and so therefore we need a two-dimensional coordinate system in which we schematically can represent the motion. An object that is thrown in the air will move along a trajectory that is a parabola. So the trajectory of a projectile is a parabola. In absence of air resistance, this parabola is nice and symmetric. When air resistance is present, it is not as symmetric as without. For our course, we are going to only consider cases where there is no air resistance. So this is a two-dimensional motion, very similar to the motion I explained in this example before. So therefore, that means that this motion can be broken into two parts, a horizontal part and a vertical part. But now, because this is a more specific type of motion, there are some specifics about the horizontal and vertical part that must be discussed. So the motion starts with some initial velocity v, which is directed at some angle theta with respect to the horizontal. And so since this is a two-dimensional vector, I can present it as a horizontal component and a vertical component. Since this is an initial velocity, I will also index the velocity with 0. And so the horizontal component is v0x and the vertical component is v0y. For the horizontal part of the projectile motion, there is no acceleration during that motion. The acceleration in x direction is 0. And because of that, the x component of the velocity is always constant. So the initial x velocity is equal to the final x velocity is constant. Which then means that the horizontal displacement x is simply calculated as v0x times t. And that's it. There is no acceleration term in this calculation because the x acceleration is 0. This is extremely important to remember for projectile motion. In horizontal direction, there is no acceleration. The velocity is always constant. Now let's look at what's happening in the vertical portion of the motion. So first, the vertical part of the motion is motion with acceleration. And so what is that vertical acceleration? Well, once you throw an object to fly as a projectile, this object is only left under the influence of gravity. And so therefore it's subject to the gravitational acceleration due to gravity. So that means that vertically the acceleration AY is equal to minus 9.8 meters per second squared. And so AY always points down towards ground during the projectile motion, always. Now, the vertical velocity is not a constant. As the object is moving up the trajectory, the vertical component of the velocity decreases until the object hits the highest point of the parabola, and then at the highest point, the y component of the velocity is equal to 0. So the vertical component of the velocity at the highest point of the parabola is equal to 0. As the object undergoes this projectile motion, it goes along the trajectory which is a parabola, and when it reaches the ground level here and hits the ground, it will have the same velocity by magnitude as the initial velocity. And it will make the same angle with the horizontal as the initial velocity. But this is only true when the starting and final positions are on the same level. So if the object lands at a higher or lower level than the launch point, then what I just said is not correct. But when the object starts and lands on the same level, the magnitudes of the initial and final velocities are the same, and the orientation with respect to the positive x-axis is the angle with respect to the positive axis is the same. One is above the horizontal, the other one is below the horizontal. So now, since the projectile motion is the sum of two motions, a horizontal and a vertical, I can apply the equations of kinematics to those two motions. For the horizontal part, we already know that the displacement is just simply the velocity in x direction times the time of travel, and there is no acceleration. So this is pretty simple and straightforward as far as calculations go. But for the vertical portion of the motion, the four kinematic equations apply, and you can use the modifications that I showed in regards to free fall for that portion of the motion. So for the vertical portion of the motion, these equations here will apply, with, again, the notion that AY is equal to negative 9.8 meters per second if you are going to use that version of the equations. If you are going to replace AY with G, then the signs must change to minuses, and G is just 9.8 meters per second squared. Now let's look at an example that illustrates the properties of projectile motion. So we have an airplane which is moving horizontally with constant velocity of 115 meters per second and at altitude of 1050 meters. Determine the time required for a care package released from the airplane to hit the ground. So here is a drawing of the problem. The airplane is moving horizontally at 115 meters per second. The care package is released from the airplane and falls towards the ground as a projectile. So initially the package is moving in horizontal direction only along with the airplane. And so the initial velocity of the package is simply its horizontal velocity Vx. But due to gravity, it starts to curve down on a trajectory that's a parabola. And so as the package is moving, at some point it will have velocity that is tangent to the parabola. It will have an x component which remains the same, 115 meters per second, because in horizontal direction there is no acceleration. And then the vertical component will be some number that can be calculated. And once the package reaches all the way to the ground, it still has horizontal component of the velocity of 115 meters per second. And now its vertical component of the velocity is the maximum possible. And therefore, if we know those two, one could calculate the final velocity of the package. The question in this problem, however, is to find the time it takes for the package to hit the ground from the release point. And so here is my table with the 5 kinematic variables. In that table, I know the vertical displacement minus 1050 meters. The minus sign again appears because the motion is in negative y direction. The acceleration AY is negative 9.8 meters per second squared. I don't know the y component of the final velocity. I know that the y component of the initial velocity is 0 because initially the package is moving horizontally. And what I'm looking for is the time it took the package to hit the ground. And so based on the information I have, which is the vertical displacement, the acceleration, initial velocity, I can calculate the time using this kinematic equation. Since the initial velocity in y direction is 0, the first term in this kinematic equation is a 0. And so the vertical displacement is simply 1/2 ay t squared. From here I solve for t, and that is square root of 2 times y divided by ay. And so when I substitute the quantities, I get 14.6 seconds. Now let's find what are the magnitude and direction of the final velocity of the care package. So the care package horizontally is moving with constant horizontal velocity of 115 meters per second. But vertically the velocity increases from 0 to some final value, which can be calculated now that we know the time for the fall to the ground. So again, I have my table with the kinematic variables. I know the vertical displacement, the acceleration in vertical direction, the initial vertical velocity, and the time of the fall. So what I'm looking for is the final component of the y component of the velocity. So then I can use this kinematic equation to calculate the final velocity in y direction. So that is equal to the initial velocity in y direction, which is 0, plus the acceleration times time. So that is minus 9.8 meters per second squared times 14.6 seconds, or that is negative 143 meters per second. What does this minus sign mean? Well, if you go back, you see here that the vertical component of the velocity, or the y component of the velocity, points in negative y direction. And so this minus sign is a reflection of that. And then now that I know the horizontal component of the velocity and the vertical component of the velocity, I can calculate the final velocity as the square root of vx squared plus vy squared. And the final velocity is 184 meters per second. The direction of the final velocity is given by the angle theta, which is inverse tangent of the y component of the velocity divided by the x component, so that is minus 143 divided by 115. That's a negative 51 degrees. What's the meaning of that sign? It means that the angle is measured below the horizontal. So clockwise direction from the positive x-axis. Let's look at a different problem now. The height of a kickoff. A place kicker kicks a football at an angle of 40 degrees and initial speed of 22 meters per second. Ignoring air resistance, determine the maximum height that the ball attains. So this is another example of projectile motion. The ball, once kicked, undergoes projectile motion. The trajectory is a parabola. The initial velocity v0 is a tangent to the parabola here. And since it is at an angle to the horizontal, it has two components. It has an initial x component and an initial y component. I can calculate those two initial components because I know the speed, the initial speed, and I know the angle that it makes with, that the velocity makes with the horizontal. So the y component of the initial velocity is equal to v0 sine of theta. That's 22 meters per second sine of 40 degrees. That's 14 meters per second. And the initial x component is v0 sine cosine of theta. That's a typo here. v0 cosine of theta, which is 22 meters per second cosine of 40 degrees. That is 17 meters per second. So now in the table with my kinematic variables, I'm looking for the vertical displacement at the highest point of the parabola. I know the vertical acceleration, negative 9.8 meters per second. That's constant and it's always the same value. The vertical component of the velocity Vy at the highest point is 0. I know that as well because that's when the projectile does not go higher anymore. The initial y component of the velocity is 14 meters per second, and I don't know anything about the time to reach the highest point. However, because I know these four parameters, I have a kinematic equation that can calculate the vertical displacement from that information. And so this kinematic equation is the one shown here. Vy squared is equal to v0 y squared plus 2 times ay times y. Since I'm looking for the vertical displacement, I am rearranging the terms to get Vy is equal to Vy squared minus V0 y squared divided by 2 times Ay. And when I replace the known quantities in that formula, I get that the height of the kickoff is 10 meters. Another question that can be asked in relation to this example problem is how long did it take for the ball from kickoff to landing? So the information that I have is that the vertical displacement is equal to 0. Why is that? Remember that displacement is the straight line distance between the initial and final positions. What are the initial and final positions here? The initial position is at the ground. The final position is at the ground. So vertically, this ball has not moved at all, hasn't displaced at all when it's all said and done. So between the initial and final positions, the ball, of course, displaces vertically, but it ends effectively at the same position when the vertical motion is considered. So therefore, the vertical displacement is 0. The vertical acceleration is negative 9.8 meters per second. We don't know the vertical component of the velocity. We know that the initial vertical component of the velocity is 14 meters per second, and we want to find the time for the ball to get from the kickoff all the way to the ground on the other side. So to solve this problem, I can use this kinematic equation. Y is equal to V0 y times t plus 1/2 AYT squared. Y is equal to 0. And then we have 14 meters per second times t plus 1/2 times minus 9.8 meters per second squared times t squared. So I can cancel t here and the second power here, and I end up with zero is equal to 2 times 14 meters per second plus negative 9.8 meters per second squared times t. And so t is either equal to 0 seconds or t is equal to 2.9 seconds. Obviously, since the ball is spending some time in the air, the time of flight cannot be equal to 0. Therefore, the correct answer will be 2.9 seconds. And now I can ask one more question, and that is, what is the range of this kickoff? Meaning, how far did the ball land from the starting point? So we know that in horizontal direction there is no acceleration of motion, and so the horizontal displacement is simply the initial horizontal velocity times time. And so that will be 17 meters per second times 2.9 seconds. That is 49 meters. That is how far the ball went after the kickoff. So this concludes that chapter. The most important points to remember is that when we have two-dimensional motion, it can be considered as the sum of two independent motions, a horizontal and a vertical, that happen at the same time. And so the kinematic equations separate for each coordinate dimension, and then you can use them in combinations to solve two-dimensional kinematic problems.